This is lecture number 8 of Econometrics Theory and Application. Stochastic Specification of Population Regression Function PRF. Here term stochastic means random variable. Assume that it is a proxy for all the omitted or neglected variables that may affect y but are not included in the regression model. Some of the variables are not included in model, and these types of variables are known as stochastic variables or random variables. For example, most of the variables are interlinked and you add few of the independent variables into the model and omit few of the variables from model, considering them as error term. Now, let's take this equation here. Y is equals to dependent variable, and this is the expected value of y given that x, and x is equals to xi. And here another equation, that is yi is equals to expected value of y given x is equals to xi, and we add and this is the regression equation, and we add the term mu I, this one, that is the error term, or we can call it stochastic disturbance or stochastic error term. So you can say that it is the proxy for all the omitted or neglected variables that may affect dependent variable, that is y, but are not included in regression model. For example, growth of wheat crop depends on 3 factors, that is fertilizer, sunlight and rainfall. In presence of these variables, you get let's say 3 metric tons of wheat during the year. By controlling same variables for the next year, you might have chance to get more tons or less tons of wheat as compared to the previous year in which you have 3 metric tons of wheat. The reason is that there are some other variables that affect the crop growth which you have not added in the model. Here we add that variable or variables in the error term, that is mu I, so that we can show that in our model there is a possibility of stochastic error. For that purpose, error term is added in the equation which shows stochastic disturbance in the model. So this equation becomes you can say that mu I is equals to y minus expected value of y given x, which is equals to xi. How do we interpret this equation? We can say that the expenditure of an individual family given its income level can be expressed as the sum of 2 components. First component is this one, expected value of y given x, which is simply the mean consumption expenditure of all the families with the same level of income, and this component is known as systematic or deterministic component. And the second component, that is mu I, which is the random or non-systematic component. By adding this mu I in the function, we can say that there are chances of errors here. And we have already discussed this one, that mu I is equals to stochastic disturbance or stochastic error term. It is a non-systematic component, whereas component expected value of y given x equals to xi is a systematic or deterministic. It is the mean consumption expenditure of all the families with the same level of income. and we have discussed this one in our previous lectures as well. Now, the assumption that the regression line passes through the conditional means of y implies that expected value of mu I given xi is equals to 0. It means that the regression line passes through the conditional means of y implies that the conditional mean values of mu I, that is conditional upon given x's, are 0. Now we are going to prove that the regression line passes through the conditional mean of y implies that expected value of mu I given xi is equals to 0. As we have already learned that mu I is the error term and yi minus expected value of y given x is the regression equation, and we add disturbance in this equation. So there is the final equation here. Now let's take the previous example that income defines the consumption expenditures of families. This is not a single variable that affects the consumption, but there are other variables also that affect the consumption expenditures apart from income. So we add mu I here, that it is a proxy for all the omitted or neglected variables that may affect y variable but are not or cannot be included in the regression model. If expected value of y given xi is assumed to be linear in xi, that is in terms of variable, then this equation can be written as yi is equals to beta 1 plus beta 2 xi plus mu I, where beta 1 and beta 2 are unknown but fixed parameters known as regression coefficients. Beta 1 and beta 2 are also known as intercept and slope coefficients respectively. Here equation, this one, shows that the consumption expenditure of a family is linearly related to its income plus disturbance. That is the error term. The individual consumption expenditures given x is equals to 80 can be expressed as y1 is equals to 55 is equals to beta 1 plus beta 2. Now we add 80 in place of x1. We are getting xi as x1 and the value of x1 is 80 plus mu I. If you remember the previous lecture, this table where I defined xi, here we are taking x1, that is 80. There are x1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we are taking x1, that is 80. If we going back to the table, this one, we have seen that there are 5 families that you can say that whose income is $80, this one. And the consumption expenditure of these 5 families are y1, y2, y3, y4 and y5, that is 55, 60, 65, 70 and 75 respectively. So in this equation, we take 80 as xi, We put 80 in place of xi or x1 in this equation, and you can say that here x1 is fixed. In this category of x1, that is 80, we have 5 families. So we make 5 equations here. You can see y1, y2, y3, y4 and y5. These are the 5 equations, as we have 5 consumption expenditures, or we are having 5 families whose consumption expenditures are mentioned in category X1, that is at $80 of income. $80 is fixed for all the equations, as there are 5 families in this category. So we have consumption expenditures, that is 55, 60, 65, 70 and 75 for these 5 equations. We have also added error term, mu as mu1, mu2, mu3, mu4 and mu5 in each of these equations. Now if we take the expected value of this equation, that yi is equals to expected value of y given x equals to xi plus mu I, we obtain, you can say this equation, that yi is equals to if we take the expected value of this equation, this one, yi is equals to expected value of y given x equals to xi plus mu I, we obtain this equation, this one, that expected value of y given xi is equals to expected value of y given xi, this function, the same function, plus expected value of error term given xi. Now coming back to the table again, on this table, look at $80, that at income level of $80 we have 5 families whose consumption expenditures are 55, 60, 65, 70 and 75 respectively. We have taken the mean value of these consumption expenditures by adding up all these 5 values. We get 325, and then we get the mean value, that is dividing 325 by 5. So we get the conditional mean value, that is 65. So 65 is the expected value of x1, and x1 here is 80. Now 65 is the single value, and if we take the average of this value again, that is dividing this 65 by 1. You can say that if we are going to take the average value of this single value, that is 65, so this is one value, and when we divide it with 1, we get 65 again. This one, as 65 is the single value, and if we take the average of this value again, that means that 65 divided by 1 is equals to 65. So the average of 65 is also 65, as 65 is divided by 1 and it is equals to 65. So this phenomena is applied over here on this part of equation. If we take the expected value of 65 here, or you can say of this function, we get the same value here, that is expected value of y given xi. So this is one value and its average value is this one, that is expected value of y given xi. That is, if we take average, that average value of 65, that is 65, we get the same value, that is 65, where a use is made of the fact that the expected value of a constant is that constant itself. So it is proved over here that the expected value of a single value is again a constant or the same value. Now expected value of y, this one, if you look here, expected value of yi given xi and expected value of y given xi, this term and this term both are same here, and if we take this term, this one, on left hand side here, so there comes minus sign with it and these two terms cancelled out. That means plus expected value of y given xi minus expected value of y given xi is equals to 0. Then we get this equation, that is expected value of error term given xi is equals to 0. Now this equation shows that if we take the average of error term given that every category of independent variable, that is xi, is equals to 0. Thus the assumption that the regression line passes through the conditional means of y implies that conditional mean values of mu I conditional upon given x's are 0. So this is the assumption which we have proved, that expected value of mu I given xi is equals to 0. Let's suppose this is not straight, but assume that this is a straight line, this one. This is the regression line, and this regression line can be made by joining the mean values of y, and if we take the average value of this mu I, that is error term, then it is equal to 0. This is considered as the assumption of regression line, that is average value of error term of the regression line is equals to 0. From all of this discussion, it is clear that this equation that expected value of y given xi, that is equals to beta 1 plus beta 2 xi. Consider this equation as A, and yi is equals to beta 1 plus beta 2 xi plus mu I. Considering this equation as B, we can say that equation A and B are equivalent forms if expected value of mu I given xi is equals to 0. But the stochastic specification in this equation, this one, has the advantage that it clearly shows that there are other variables besides income that affect consumption expenditure and that an individual family's consumption expenditure cannot be fully explained only by the variable or variables included in the regression model. So this is shown by this error term, that is mu I.